Hi everyone, I'm Wang and I'm happy to share our work, DeepC2, an AI-powered command and control on online social networks. The presentation includes 4 parts, and we go to the first part now. We know that command and control is essential in an attack, especially in some advanced malware scenarios. The attacker needs to send the commands to the malware, and the malware needs to send feedback to the attackers. They need a way to communicate with each other. So what is a command and control? Command and control, or C2CC, usually contains 3 main components: the attacker or controller, bootmaster, the malware or bot, and the CC channel. The attacker publishes the command to the channel and the malware fetches them. The process for the malware to find the commands is called addressing. At first, the attacker sends the command to the malware using IRC, HTTP, and P2P networks. They face single-point failure or SIBO attacks. However, they are still in use today. But as time goes on, attackers continuously use new technologies to build a C2 channel. The first web service-based C2 channel appeared in 2009, and it has been favored by attackers as soon as it appeared, and has been widely used in attacks. Now, what are the advantages of a web service-based C2 or an online social network-based C2? They nearly never go offline, and visiting such web services is allowed by the local firewall. They have a huge user base, so the attackers can hide among them. So over the years, they were abused in attacks. However, they also have 2 disadvantages. First, the addressing process is reversible. Whether they use static methods like IP, ID token, or dynamic methods like DGA, once a security expert reverse engineers a malware sample, all the information will be exposed. The defender can calculate the attacker's accounts and block them before the commands are published. How to eliminate the reversible hardcoding is the first problem. Then the commands are abnormal contents on OSNs, whether in plain text or encoded or encrypted forms. They differ from regular contents on OSNs. They may trigger restrictions on the attacker's account or commands. So how to eliminate the abnormal content is the second problem. The way to solve these 2 problems is to convert the reversible hardcoding to irreversible methods and turn the abnormal content to readable. How to do that? In the AI era, attackers may use methods in AI to solve them. A neural network may solve the reversible hardcoding, and data augmentation with hash collision may eliminate the abnormal content. Then what to do? Let's take a look at what information is included on the OSNs. Take Twitter as an example. There are images, including header photo, avatar, shared photos, comment, and retweet with photos. There are also text, including names, screen names, bell, tweets, comments, and retweets. There are also text in the pictures. We know that AI is very capable in the field of image processing. Therefore, a neural network can be used to identify images as a means of addressing. Commands can be hidden in readable content using data augmentation and hash collision. Then why do we use a neural network? First, they are poorly explainable, and the calculation process is hard to reverse. Combined with the intention to introduce the losses, it's hard to get the attacker's identifiers in advance. Then the neural network is for tolerance to the inputs. we know that images uploaded to the online platforms get compressed, and a neural network will ignore the changes. Then the neural network has also a good generalization ability. A cat that does not appear in the dataset is also a cat, not a dog. So it can recognize the attacker accurately and not mistakenly regard someone else as the attacker. Then how to use it? We also take Twitter as an example. First, the attacker needs to train the neural network model to recognize images and prepares a group of photos. Then the attacker extracts feature vectors from the photos and publishes the malware with the model and vectors. When they need to issue a command, they change the avatars to the prepared photos and post tweets on Twitter. The malware will create the avatars and tweets to find the attacker and get the command. For the same model, the attacker and malware use it differently. The attackers use the model to extract feature vectors. The model accepts images as inputs and outputs the feature vectors. The model accepts two inputs for the malware: an avatar from the Twitter user and a vector from the attacker. The model will produce a distance that measures the similarity of the inputs. If the distance is below a threshold, it's considered that the attacker is found. Then there are so many Twitter users. How do they meet? We use Twitter trends as the meeting point. When it is time, the attacker and malware visit Twitter trends and select the trending topic. Then the attacker creates tweets to the topic, generates command-embedded tweets, and posts new tweets. At this step, the attacker should have selected the photo and set it as an avatar. For the malware, it will wait for 5 minutes and then create tweets and avatars to the topic. They calculate the distances between the avatars and vectors to find the attacker. If the attacker is found, the malware decodes the tweets to get the commands. Then why Twitter trends? Besides the meeting point, it contains numerous discussions on topics, and the attacker can hide among them. Then it changes with the tweet volume and is updated every 5 minutes, which is not easy to predict, so we use Twitter trends. Now that attackers choose Twitter trends to publish the commands, how can they convert the commands into readable tweets? They can use hash collision. First, the attackers split the command into two byte chunks and express them in hex or binary form. Then the attackers calculate the hashes of the tweets and compare the first two bytes with the command chunk. If they are the same, the tweets are selected. If all command chunks are collided, the hash collision succeeds. The attackers need to post the tweets in an order so that the malware can recover the commands correctly. Hash collision needs vast tweets. That is why the attacker also needs to create the tweets in the topic. But the created tweets are still insufficient. So the attacker needs to generate new sentences for hash collision. How to generate tweets efficiently? Data augmentation techniques can help. They do physical transformation to expand the dataset. In this scenario, either data augmentation either use 4 techniques. Here's an example. For this tweet, either can generate similar-looking but not the same sentences. The changes in the new sentences are bold. New generated sentences may not be correct in grammar. However, it is also the case on Twitter. So these sentences are acceptable. So here's the workflow when issuing the command. the attacker could twist, clean twist, generate more twists, hash collision, and post the twist. The malware could twist and avatars, calculates the distances, calculates the hashes if the attacker exists, and get the command. Here's the implementation. We use CMS neural network in this task. The CMS N is effective in measuring the similarity between two inputs. The two inputs will fit into two identical neural networks. The similarity can be measured by calculating the distance between the two outputs. Inside the SNN is a CNN. Here's the structure. It accepts a 3-channel 128-pixel image as the input and generates 128 outputs at the feature vector. To train the model, we use the avatars from Twitter users as the dataset. Level 0 is for similar inputs. They are avatars from the same user but in different sizes. And level 1 is for different inputs. They are avatars from different users. Finally, we got the SN model in 2.42 megabit. We conducted the experiments on Twitter. We used 8 virtual servers to simulate the malware and the attacker around the world. The attacker and the malware used the last trending topic about 10,000 discussions from Johannesburg as the keyword. The malware waited for 5 minutes after choosing the topic, and the attacker posted the tweets within the 5 minutes. Experiments show that each malware can obtain the commands correctly, but the time cost varies. The minimum time cost is 5 seconds, but the maximum is 4.5 minutes. The malware needs to cool the avatars, and the time cost depends on the network conditions. The average time for the attacker to collect tweets and get the final tweet available is 13.8 seconds, which is also acceptable. Then comes the evaluation. The evaluations are all completed in the same virtual server as above. There are words, deletions, and swaps in the edit process. If the training words are changed, the malware can find the attacker using the topic. Therefore, we need to make sure the new sentences with the exact keywords are sufficient for hash collision. Besides, we need to test the efficiency of data augmentation. We collected 79 topics and coded 1,000 tweets per topic. After cleaning them, we generated 50 sentences from each remaining tweet. In the 79 topics, 55 contained only one word and 24 contained more than one word. After augmentation, 89.54% of the new sentences contained accurate keywords for the single-word topics and 77.55% for the multi-word topics. It's acceptable. The time cost is linearly related to the number of new sentences. According to the test, generating the sentences cost 3 to 10 seconds. It is acceptable for the attacker to prepare sentences for hash collision. Then comes hash collision. We test the time cost and success rate. We expand the sentences by adding punctuations and converting cases, and this gives us a multiple of the number of sentences. We used more than 400,000 sentences and 100 commands and calculated their SHA-256 using HashLab in Python with a single thread. The results show that it costs less than 1 second to calculate the hashes. If there are more than 140,000 sentences, the success rate is higher than 75%. If there are 330,000 sentences, it will be nearly 100%. In the experiment on Twitter, we got about 220,000 sentences on average and a success rate of 90.28%. It's acceptable. Then the time cost for the avatar recognition for the malware. We used for 40 feature vectors and 1,000 avatars in the test. The average time cost for the malware to extract the 1,000 feature vectors and calculate the distances is 11.92 seconds. It's also acceptable in such a hardware condition. It also confirms that the time cost in the experiment on Twitter is for coding the avatars. Then comes the tweet coding. In the Twitter experiment, the malware waited for 5 minutes after choosing the training topic and then coded 1,000 tweets. So, is it suitable? We test how many tweets the malware should code with different waiting times. The results show that 1 hour after the attacker publishes the tweets, the malware can still find the attacker within 1,000 tweets with a high probability. This is acceptable. The result will be different if the attacker chooses topics from different areas with different discussion volumes and puts tweets in at different times. The attacker can customize the parameters. This part is the security risks of the proposed C2. We analyze from the defender's perspective. A defender can reuse the avatars from the attackers. In our design, each avatar and vectors use the new ones to prevent replay attacks. Therefore, this will not affect the malware that is always online. However, for the malware that goes offline and misses some commands, they will recognize the defender as the attacker and get incorrect commands. Therefore, authentication between the attacker and malware is recommended. Besides this measure does not affect the C2 channel. The defenders can try to collate for an avatar. It sounds feasible, but it's hard practically. We analyzed the composition of the vectors. The numbers constitute a continuous interval, which is hard to call it. However, we still had a try. We made more than 600 million calculations on the distances between the code avatars. 2050 avatar pairs have a distance below 0.02 and 81 pairs below 0.01. By analyzing the pictures, we found these shared similar styles in that they all have a large solid background, especially white. As the avatars are prepared by the attackers, they can avoid this type of photos. Defenders may train again with saved avatars to generate similar images. As the avatars can be animals, plants, arts, the training target is too divergent to be capable of GAN. Additionally, training a GAN needs numbers, it needs a lot of data, and the attackers' avatars are insufficient for building such a training set. Defenders have access to vectors and models, so they can recover them and derive an image that can produce a similar vector. We assume that defenders treat the neural network as a decoder and build a corresponding decoder to generate the pictures. We trained such a decoder and generated the images from vectors and calculated the distances. However, the lowest distance we got is larger than the threshold. It did not succeed. Defenders can attack the neural network model to let the malware make incorrect decisions on the attacker's accounts. The target of this attack is a model, so it may affect some malware but does not influence the ones in the wild. As the model and feature vectors are known to the defenders, it's a white box non-targeted adversarial attack in this scenario. Defenders can generate an adversarial sample to fool the model. However, adversarial attacks aim at misclassifying the original target. Although there are 128 outputs, they do not represent 128 classes. The changes to the vectors will result in a higher distance. Therefore, it's not suitable to attack the C2 in this way. There are also some ways to enhance the C2 channel, such as using longer feature vectors and introducing more losses in image processing. It will make the above attacking methods more difficult. For addressing, the attacker can choose more topics to publish the commands, use other fields like comments and bell, and use more platforms. It will increase the robustness of the C2. The attacker should maintain some Twitter accounts for publishing commands. They can use high-value accounts and maintain them by imitating normal users to use special behaviors. In this part, we discuss the possible countermeasures. The attacker uses AI to enhance the C2 channel. Therefore, detection can be performed on the other two sides. Behavior and traffic analysis methods can be applied to detect the malware. There are periodic behaviors of the malware. This series of operations can make up a behavior pattern. OSNs can detect the anomaly behavior of the accounts and cluster them through behavior similarity. They can also apply more risk control rules. For example, adding verification on risky operations for users and limiting content exposure for low-credit users so that the malware may not get the tweets from the attackers. Last, collaboration between the security community and OSN platforms is necessary. They share the malware samples, and OSNs check the newly uploaded avatars. It can detect the attacker in real time. It may cost a huge calculation, but is an effective way to mitigate this attack. So here comes the conclusion. In this work, we propose to solve the reversible hard coding by using a neural network and eliminate the abnormal content by hash collision and data augmentation. We performed the experiments on Twitter and evaluations on each component to prove the feasibility of this threat. We also discussed possible countermeasures to mitigate this threat. Thanks for listening.